Hi everyone, it's time for some review of our functions unit. Here we go, let's jump right in. Okay, we're going to begin by looking at identifying functions and our ability to know when something is a function or not. So if we're set up with a situation where we can actually see a graph of something and see that it's a function, we can use the vertical line test. So with a vertical line test, we just have to have a vertical line. You could use a ruler or anything like that, and we're going to pass it over our function. If our vertical line only touches the function in one place at a time, then that means that it is a function. So this for first one, we can only touch it in one place at a time. Our second one, you'll see I can touch it in two places at a time in several spots along there. My third one, C, I can touch it in two places at once. And my fourth one, I can only touch it in one place at a time. So that means when we're looking at these ones, this one's a function and this one's a function, and these two are not functions. So that's our vertical line test. That's our first way to identify functions. The next way we might try and identify functions is if we got a mapping diagram. So with a mapping diagram, we're looking to see if any of our x values map to two different y values, or any of our inputs map to two different outputs, or any of our independent variables map to two different dependent variables. So this is the same thing, but just another way of looking at it for mapping diagrams. So on the first one here, I notice that my value of 2 maps to two different possible, um, my input of 2 maps to two different possible outputs. So this one is not a function because there's an input that can map to two different outputs. My next one, each input has a single output. So you'll notice that for the one, it is an output of two different things, but that's fine. Um, as long as each input has a single output. So this is a function. Okay, we could also have a table of values. So when we're looking at the table of values, my first one here I see that for my x values, my 4 different inputs, I don't have anything where there's a single input that has two different outputs. So this is a function. My next one, unfortunately, doesn't have that. 0 as an input could have two different outputs, and 3 as an input could have two different outputs, so this one is not a function. And my third one, all of my inputs have a single output. It happens to be the same one, but I don't have any situations where a single input has two different outputs, so this one does count as a function. The next topic we're going to look at is domain and range. So remember, domain is all of our possible x values, and range is all of our possible y values. When we're saying the domain and range, we've got a specific kind of notation that we use, and specifically we're going to write it. So we're going to look at 4 of these. For our first one, I've just got a set of ordered pairs. This would be very similar if I had a table of values, how I do this. So this is nice and easy. For my domain, I'll just use a D. I'll use a little curly bracket. I'm going to start my range the same way, but with an R, and do a little curly bracket. Now my domain is all my possible x values. That's 4, 6, 10, and 2. Now sometimes you'll see these written in order. It's fine either way. I didn't happen to write them in order, starting with 2, 4, 6, 10. Either is okay because I've listed all the possible x values in this function. For all my possible y values in my range, it's going to be 2, 3, 5, and 1. Those are all my possible y values. Okay? And just to make that really clear, there's my x values, and here's my y values. Okay? All right, let's go to a function. This is it comes from our parent function. So our parent function would be y equals the square root of x. This one happens to have a plus 4 in there, which means it's transferred 4 units in the negative direction. So instead of looking like this, it's actually going to be moved over 4 units in the negative direction. So let's say it would look something like that. And on our graph, this is going to be our spot where we got negative 4 on our x-axis. Okay, so for our domain and range, let me just get a little space here to put that. go. So say, okay, my domain, that's all my possible x values. I could have any number along this curve, right? So the first thing I gotta say is that x is an element of real numbers, meaning there could be any of the values in there. But I notice I can have, because this keeps going on forever, I can have any positive x value um, to the right, but I can't have anything that's less than -4. So I'm going to say the domain can be anything such that x is greater than or equal to -4. That's how I do my domain for that. For my range, what are my possible y values? Kind of similar. First I say y is an element of real numbers, right? And I'm going to do that for anything that's not just like points, right? Anything that is a line or a curve, I could choose any of the spots along that line or curve. So I got to say it's an element of real numbers, such that y is going to be greater than or equal to 0. I notice my y values can't be in the negatives. They got to be 0 or more, so greater than or equal to 0. Okay, so that's my first two. I'm just going to save this, and we'll try the next two. All right, let's get rid of this screen and see what else we got here. Okay, looks like we got a quadratic function and a reciprocal function. So first I'm just gonna like do a quick little sketch of what these would look like. So normal quadratic looks just kind of like this, right? It keeps going. But this one has a +2 added on the end. So that means it's actually going to be moved up 2 spaces. So something like this. It's been translated up 2 spots. So on my graph, I could say, okay, this is a y value of 2. So let's do my domain first. Now, a domain for quadratics is actually really easy. X is an element of real numbers. We know we got to do that each time. But I don't have to do it as such that, because it could be anything. For my x values, it's going to keep going to the left and keep going to the right to infinity. I could put in any x value into my equation, any input into my x, and I would get an output. So I could choose any value. So any x is good. And this is true of any quadratic like this. My range, again, I got to say y is an element of real numbers. But in this case, I got to say such that y is greater than or equal to 2. Because I see I don't have anything below 2. There's nothing, all the space down here. You can't have any values there. So it's got to be greater than or equal to 2. Anything above that. Okay, my reciprocal function, when I graph it, it looks kind of like this, like that, and like that. Okay, that's not the greatest, but let me give that another crack. See if I can improve that a little bit. A little more careful, like that, and then kind of like that. Okay, that's a little better anyway. For my reciprocal function, I notice that it is moved. It's got a +3 next to the x, and of course that means I'm going to be moved 3 spaces in the negative direction. So 1, 2, 3, 1, 2, 3, kind of like that. And so that means instead of this spot in the middle where we never quite hit, instead of that being 0, that's going to actually be at 3, -3 on my x-axis. Okay, so let's do our domain and our range. So domain, possible x values. Well, really, x is an element of real numbers. And you could have anything except there's one catch. X cannot be equal to -3. Because my function never goes there. It's on either side, but it never gets to -3. And my range, y is an element of real numbers. And same deal, I notice that it never quite touches y equals 0. So y cannot be equal to 0, but any other y value is a possibility. Okay, so that's my domain and range, and that's the notation I use for my domain and range. Let's keep rolling right along here. We're going to do function notation next. So I've got two functions, got an f at x function and a g at x function. I know when I sub anything in, I'm going to have to sub in here to show the number I'm subbing in, and then anywhere I see an x, I would substitute in that same thing. Same thing for g at x. Anywhere I would see an x, I would sub that thing in. Okay, so these are my two different functions. Let's try some examples here. Okay, so my first one is f at 3 plus g at 1. Basically that's saying with an input of 3, what is my output? And that's a number that I'm going to put there. And then with an input of 1 into my g function, what's my output? I'll put that number there. So let's figure this out. Let's get a nice purple marker here. So f at 3, I'm going to take this function right here and I'm going to sub a 3 in where I see that x. So it's going to be 2, and there's a 3 that goes in where I saw the x, and that's good. Okay, now for my other function, g at x, that's right here, I'm going to put a 1 in where I saw that x. So I'm going to go plus, instead of x squared, I'll have 1 squared minus 3. Okay, let's continue on and figure this out. 2 times 3 is 6, minus 1, plus 1 squared is 1, minus 3. So it looks like my answer is going to be 3. So f at 3 plus g at 1 works out to be 3. Okay, let's try my next one. G at y plus 1. I'm going to take my g function and I'm going to substitute in y plus 1 anywhere there was an x. So I took where that x was and I subbed in a y plus 1 instead. Now I can actually FOIL this out, right? Because that's just y plus 1 times y plus 1. I'm not really focusing on algebraic expressions now, so I'm going to do that part kind of quick. And then I can simplify. So there we go. This is what I get when I substitute y plus 1 into my function, anywhere x is. Okay, my last one, f at g at 4. So this kind of thing I got to work from the inside out. I got to figure out what g at 4 is, and then I can substitute that into f at whatever that number is. So let's do this in two parts. Let's start just by figuring out what g at 4 is. So that's going to be everywhere I see an x, I'm going to put in a 4. 4 squared is 16, minus 3 is going to give me 13. So now I need to find, I'm just going to put a line there to show I'm going on to something new here. So now I've got to find f at 13 because that's what g at 4 was. So f at 13. So what was my f function again? 2x minus 1. So I'm going to go 2 times 13 minus 1. So that's going to be 26 minus 1, so that's going to be 25. So my final answer is 25. F at whatever g at 4 was, g at 4 was 13, so f at 13 is 25. Okay, so that's my function notation. And you might have to work with those in a whole bunch of different ways. We had like adding here, but you might be adding some and subtracting some. If you need to do them one at a time and then add and subtract all the pieces, that's a great way to do it. Okay, next I've got transformations of parent functions. So my parent functions that I'm used to seeing, I've got things like f at x equals x squared, that's a quadratic. I've got things like f at x equals the square root of x, that's a radical function. Let's just do what they look like. Quadratic looks like that, radical function looks like that. Sorry, it doesn't go down, it kind of just like flattens out. I've got my reciprocal function, which I already talked about, that's 1 at x. It looks like that and like that. And what's the one I'm missing? Oh, my absolute value function is my other parent function, which has those straight lines, and that just means it can only be positive numbers. Whatever you substitute in for x, you turn that, whatever's in there, in those lines, you turn it positive. So instead of being a straight line, it's like a v. Okay, so those are my parent functions. Now it's really important when I'm looking at transformations. I look at this. This is not a function. This tells me what transformations to do to another function. And I can tell because there's this f right there, okay? So when you see something that looks like this is just a description of transformations that you would do. Transformations that you would do, okay? So we got to determine the equation of this parent function, f at x equals x squared, my basic quadratic, and then I got to do all those transformations to it. So what are my transformation parts? Well, it looks like I'm going to multiply my y values by a half, so that's a vertical compression. Looks like I'm shifting to the right 2 and up 4. We'll talk more about those transformations in a minute, but for now we just want to focus on the equation. So I'm starting with my basic equation for my x squared, but what I see is that instead of x, I'm going to put x minus 2 in the bracket. So let's start with that. I've got my x, where my x squared would be, but instead I'm going to put an x minus 2 in there. I'm going to have a plus 4 on the end, and in front of where my x would go, I'm going to put a 1/2. So this is my parent function of my quadratic transformed under that transformation. Let's try another one of our functions down here. Let's try a reciprocal function. And what we're going to do is we're going to do a couple transformations to it. We're multiplying our y values by 2, so that's a vertical stretch. And we're moving 3 units to the left in the negative direction. Okay, so how do I do this? Well, my function is going to be 1 over x, but where x is, I'm doing this stuff, so I'm going to go x plus 3. Okay, and I'm multiplying the whole thing by 2, so I could put a 2 out front, but really when you multiply a fraction by a whole number, you just multiply the numerator by that, right? So I'm going to multiply 1 times 2 and just put the 2 up there. So this function shows these transformations. Okay, this is how these transformations would look when we write the equation for this specific function. Okay, let's keep on rolling. Let's try describing these transformations. This is for each function, identify the parent function and describe how the graph of the function could be obtained from the graph of the parent function. Okay, so I need to describe the transformations and what they're actually going to do. First things first, let's just describe the parent functions. I can see that this one is, my parent function is going to be, we used to write y at x, you could write f at x for this one now. It's just going to be x squared because I can see its basis is an x squared. Okay, this one, the basis is the radical function, and this one, the parent function, is the absolute value. I can tell because it's got those absolute value lines, and I can tell because this one has the radical lines. Okay, so those are the parent functions for each of these. So now I need to describe what you would do to the parent function to have these changes. So here's what I see. The first thing I see is there's a negative 2 out front. Okay, the 2 means I'm going to multiply. So it's a vertical stretch and a reflection in the x-axis. That's what the negative does. But I'm going to describe what you'd actually do. You're going to multiply your y values by negative 2. So whatever's in front there, that's what you do with your y values. Okay, so I'm going to multiply my y values by negative 2. That's going to stretch it and flip it in the x-axis, be a reflection in the x-axis. Here's my next one, right? It's inside the bracket in front of the x. What we're going to do with this is we're actually going to divide our x values by whatever that is. Now, dividing by an eighth is the same as multiplying by 8. So I'm going to say, I'm going to divide x values by 1/8. And we know that that would be the same as multiplying by 8. Okay, last, but certainly not least, well, maybe least, because it's the easiest, is this one right here. I'm going to add to my y values. So add 1 to y values. Okay, that's just a vertical shifter. Okay, next one. Let's see what we got. Oh, you know what I noticed with this one? I noticed that this one could be factored inside. So I'm going to redraw my radical here. I'm going to common factor out a 3, and then I'll have, actually I'll common factor out a negative 3, and then I'll have x minus 3, like that, minus 2. So I factored it out. That's going to make it easier to see what transformations are happening. Let's start with our blue marker and see what's happening out front. There's nothing multiplying it out front. So let's go to our next one. Looks like we're going to be dividing all of my x values by negative 3. So we'll divide our x values by negative 3. Next, let's do, what's another color I could use for this? Let's do a nice light green. Let's hope this shows up for this one right here. That's going to be my horizontal shifter. It's negative, which means I'm moving in the positive direction, which is to the right. I'm going to add 3 to x values. It's going to shift it to the right, 3 spaces. And what color is it using for that? I'm going to do this one right here, and I'm going to subtract 2 from my y values. Okay. Last one here. Let's just do this one verbally because we've written all the other 2 out. So we can just kind of talk about this one. First in front, I see a 1/2. I'm going to multiply all my y values by, oh, first I got to factor this, right? So I'll factor a 2, and then I'll have x minus 1 plus 3. There we go. Okay, so what are my changes here? This half out front, that's going to multiply all my y values by a half. That's the same as dividing my y values by 2. Then I've got this 2 that's in here with the x value. I'm going to divide all my x values by 2. So that's going to be a horizontal compression. And then I got this minus 1. That's going to move me to the right in the positive direction. So I'm going to add 1 to all my x values. And then this one I'm going to add 3 to all my y values. It can be useful to remember that stuff on the inside, you do the x values and you do the opposite operation, dividing by 2 and adding 1. And stuff on the outside is done to the y values and you do what you see. Multiply by a half, add 3. Okay, so that can be kind of an easy way to remember it. All right, rolling on. Let's do inverse functions. Getting pretty close to the end of our function stuff. Inverse functions is the last topic, but it's a bit tricky. So we'll start with some linear stuff and then we'll move on to quadratics. So here's 3 ways we can find the inverse of a function, right? First one is just you have a table of values. You switch your x values and your y values, you just flip the columns. That's one way to find the inverse of a function. Next one is to graph it. You put a mirror line at the line y equals x. And I want to be really clear about that mirror line, okay? Let's say this is my coordinate grid. The line y equals x goes like this. Okay, so that is your mirror line. And then if something was over here, you'd say, okay, let's go straight to the mirror line. It's going to appear on the other side. Okay, that's how we do a mirror image. Say one was here, go straight to our mirror, and it's going to appear on the other side here. That's how we use our mirror line. You can also just take the coordinates of the point. Say the coordinates of this point was, I don't know, say like -2 and 4. I can just switch those coordinates, so this would be 4 and -2. And that would be a way to find it. Okay, so you can graph it using the mirror line, or you can you do it with an equation. With an equation, you just switch your x and y values, and then you manipulate it to re-isolate y, and that's your inverse function. So let's find the inverse of some functions. We'll start with some linear ones. Okay, so here is f of x equals 4x minus 2. First thing we're going to do, let's change it back to y equals 4x minus 2. Now let's flip our x and our y. So I'm going to put a line here showing I'm doing something new. This is not an equal thing. I'm going to put my x here and I'm going to go 4y minus 2. So those two are not equivalent, but I'm trying to find the inverse. Now let's manipulate this to get y by itself. Let's add 2 to both sides. Get rid of that 2 on the right, and then let's divide both sides by 4. So this is going to be x plus 2 over 4. Now you might say, hey Mr. Roy, I would really like to write this as 1/4 x plus 2 over 4 is a half. because that's a nice way to do a straight line, because then you have your slope and your y-intercept, and if you want to do it like that, that's awesome. I'm happy with either of those. So then we'll say, okay, let's write it in inverse notation. F to the negative 1 x equals x plus 2 over 4. Or maybe you like to write it the other way, and that's okay too. Okay, so that's my inverse function. Let's try this other one over here. Let's do our inverse. So we're going to say, okay, I'll write it as y equals 1/2 x plus 3. Now we'll switch our x and our y. Let's isolate y. Let's subtract 3 from both sides. And now to get y by itself, let's multiply both sides by 2. And now to simplify, we could multiply through the brackets. So 2 multiplied through the brackets is 2x minus 6. And now let's write it in its inverse notation. So linear, not too bad. That's how we can find the inverse of a function using the equation. Let's try using a table of values. So here we got a function and we got a table of values for the function, right? So let's see where some of these points are on here. Let's do that one because it's a vertex. So that is, let's give me negative 2 and y value of 3. Let's do one right here because that's on a nice point. So that's negative 1 and 0, y value 0. Let's do this one here on the opposite side. That'd be a good one to do as well. Negative 3 and 0. And let's fill out one more. Let's find somewhere where it crosses the axis here, or crosses a grid line. Let's do, I don't know, this one right here. So that's an x value of 0 and a y value of negative 9. Now if I want to find the inverse, I just need to flip the coordinates. Let's do that in green. So 1, 0 becomes 0, or sorry, negative 1, 0 becomes 0, negative 1. Negative 2, 3 becomes 3, negative 2. 0, negative 3. Negative 9, and 0. So let's see if I can plot this on here. So I might not be able to find space for all these things, but I'm going to try. So 0, negative 1 is going to be right here. So this is going to be my my point from right over here that I've mirrored. Now let's try 3, negative 2. 1, 2, 3, negative 1, negative 2. That's going to be right here. 0 and negative 3. 1, 2, 3. That's going to be right here. And negative 9, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to be right here. Okay, so what does this actually look like? Well, let's see which one was my vertex. Negative 2, 3 was my vertex. So it's the one that's going to be 3, negative 2. So this is my new vertex right over here. And my inverse is going to go like this. So it's kind of like a quadratic that's been flipped on its side. Okay? Or you could think about it as rotated 90 degrees to the left. Now I could have done that with a mirror line, right? That would be a totally fine way to do it. So a mirror line is going to go like this, in the other direction like this. Probably should have done that with a line tool, but at that point I'm just looking opposite. So you'll see this point right here and this point right here are on opposite sides of the mirror, a half a square away. How about this one? How do we get straight to the line? 1, 2, and a half. So a half, 1, and 2 would take us over here. So these are on opposite sides, and these ones are on opposite sides. Okay, so all the points are mirrored on the other side of that mirror line. That would be another way to do it without the table of values. We just take our first one and flip it. All right, so let's try putting a whole bunch of this together with a quadratic. Here's a function below. F of x is x plus 3 squared minus 1. We're going to identify the parent function. We're going to describe the transformations from the parent function. We're going to determine the equation of the inverse. And we're going to graph both the original and the inverse on our graph. I think it might be a good idea right now to stop the video, see how much of this you can do on your own. Okay, you're back. After giving this a shot, let's jump in. First of all, identify the parent function. I'm just going to do that right up here. I'm going to say, okay, our parent function is a quadratic. I can tell that because it's squared right here. So our parent function is just going to be x squared. Describe the transformations from the parent function. There's just two of them. So I'll do b right here. The first one is my plus 3. I'm going to move 3 units to the left. That's the negative direction. You could also, to get there, you're just subtracting 3 from your x values. And I'm going to move 1 unit down. So notice before I described it differently because, let me find it right here. Here it said, describe how the graph function can be obtained. So I'm describing what I would actually do to the values. Here it's saying describe the transformations. I mean, it's semantic difference. I don't really care how you talk about it. If you can show me that you know what you're doing, I'm happy with either of those, right? I'm interested in you showing me an understanding of what's happening, not that you're going to use the exact language I asked you to do. So just show me you know what would happen to them, and that's fine. So good, we did B. Now C, determine the equation of the inverse. Let's change pen colors so we got this nice and organized. I'm going to switch my values. So I'm going to say x is going to go here. We're going to have y plus 3 squared minus 1. Now we need to rearrange to get y all by itself. That's a little tricky. Let's start by adding 1 to both sides. So we'll have x plus 1 equals y plus 3 squared. Now let's take the square root of both sides to get rid of this squared on the right. And we're going to end up with the square root of x plus 1. Of course, that's got to be plus or minus, right? Because when you're doing a square root, what's the square root of 4? You'd say it's 2. Well, it could be 2 or negative 2 because both of those numbers can multiply to be 4. Multiply together to be 4. So we don't know if it's plus or minus. The plus part is going to do the upper part of the curve. The minus part is going to do the bottom part of the curve. And now let's get y by itself by adding, subtracting 3 from both sides. So I'm going to have plus or minus of this, x plus 1, and then I'm going to have minus 3 at the end. So my inverse function is going to be like this. The inverse function is going to be plus or minus the square root of x plus 1 minus 3. So this is my normal function, which is my radical function, but it's shifted 1 unit to the left and 3 units up. Let's draw my, my quadratic here first. Okay, so with a normal quadratic, I would say I start out at the origin, and then I got 1 point here at 1, 1, and negative 1, 1, and 2, 1, 2, 3, 4, and negative 2, 4. So that's my normal quadratic, and I'm going to draw that in like this. Very nice. But now I want to do my shifting. So I'm actually going to grab all of this, and I'm going to group it together. Give me a moment to take care of that. We'll group everything. And you'll be able to see quite nice and easily how this shifts. Okay, so there I am back set up as my regular y equals x squared. Now I know I'm supposed to shift 3 units left and 1 unit down. So let's grab our graph here and let's go 1, 2, 3 units left and 1 unit down. So it's going to look like that, right? This is my function right over here on the left. F of x equals x plus 3 squared minus 1. Now we want to do the graph the reciprocal. There's a couple ways we could do that. Let's start just by looking at the mirror line. That might be a nice, easy way to do it. So here's our mirror line. Okay. And what color should we use? Let's use green because that's what I used to write it. Okay, so looks like this vertex point is 1 square away. So I'm going to put the mirror of that one over here. Looks like this one is also 1 away, so I'm going to put the mirror of that one over here. This one is 1, 2 away, so I'll go 1, 2, so that one's over here. I can already see this is tipped on its side, right? This one is 1, 2 squares away, so 1, 2 squares is right here. And this one is 1, 2, 3, 4 to the mirror line. 1, 2, 3, 4 to the mirror line right here. So there we go. Now I could also have done this by just looking at the coordinates of the points, right? So let's say I have a point here that is, I don't know, this one right here. It's -1, 3. So to find the point that's my corresponding one on my reciprocal function, or my inverse function rather, it's going to be 3, -1. So 1, 2, 3, -1. That's right here. So I could have just picked the points and then flipped the coordinates, or I could look at the mirror line and do it that way. Or I could say I'm going to take my regular radical function. I'm going to draw the upper line and the bottom line, depending on whether I'm using the plus or the minus. But I'm then going to shift it. I'm going to shift it around. I'm going to shift it 1 to the left and then down 3. And that would get me to the same place as well. So several different ways. You can just choose whatever you're comfortable with to graph the inverse there. So that would be doing the inverse of a quadratic function, both finding the equation and graphing about where, saying where it would be. Okay, so we're going to stop there. That's it for functions. I hope this review has been helpful, and now it's time to do a little bit of practice to make sure you're feeling comfortable with your function stuff. Go for it.